sticks, could a stick snapper snap if a stick snapper could snap sticks? A stick snapper would snap all the sticks it could snap, according to Michaelis-Menten kinetics. Enzymes are biological reaction speeder-uppers or catalysts, and so they help make happen things like putting together our DNA and making our proteins, breaking down sugar that we eat, building up fat, doing all of these various things. And they can have all these complicated mechanisms, and they can do all these various things, but we can kind of simplify things down by imagining that there's something like a stick snapper. And so if we have this example of a stick snapper, and now we want to say, okay, so our sticks would be something like our substrate. So this is the thing that an enzyme is going to act on. So our enzyme is going to bind to the substrate, and now you have an enzyme substrate complex. The enzyme is then going to break the substrate. Do the easy part. The enzyme is then going to break the substrate, and now you have your products or products. And so we can define this relationship where we're talking about the concentrations of the enzyme, so the free enzyme, the free substrate, and the enzyme substrate complex, and the products. And by measuring these and also measuring the rate at which these products are being formed, we can tell information about the enzyme and how the enzyme is acting towards the substrate. And in the case of the stick snapper analogy, how much sticks you're snapping, so like how good you are at snapping a stick, is going to depend on how well you can bind that stick. So the affinity for the substrate. This is a value called the Km, or the Michaelis constant. So each enzyme is going to have a Km towards a particular substrate, and that represents, in the most simplistic way, how good it is at like binding it and how strongly it'll bind it, as opposed to just like letting it go, or just like not grabbing onto it if it comes by. Then it's also going to depend on how well it can snap the stick. So every time it binds a stick, it's then going to have the chance to snap it, and how well good it is at going and actually snapping it, that is defined by this like catalytic rate constant kcat, also called like the turnover number. So how many sticks you end up snapping and how fast you're snapping these sticks is going to depend on things like the kms, how well can you bind onto this, and how well can you then turn it over. And so we can talk in terms of this Km and this kcat in order to kind of talk about like how good an enzyme is towards a various substrate. And we can get information about these by measuring the enzyme kinetics. So by measuring like the speed. So kinetics is referring to speed, and the speed at which the reaction happened, the reaction rates are going to depend on those constants, the Km and the kcat, as well as concentration. So they're going to depend on things like the concentration of substrate, because the more substrate you have, then the less the Km is going to matter, and the less substrate you have, the more the Km is going to matter. And in either case, the amount of substrate you have is going to influence the amount, the rate of the reaction. And then the final rate of the reaction is going to depend on how many of the stick snappers that you have in there. So it's going to depend on the amount of your sticks, and so the substrate concentration, as well as the amount of stick snappers, so the enzyme concentration. Those are going to influence your final maximum velocity, the fastest speed that you can work at. So this Vmax. And so the Vmax is kind of representing if you had a whole group of stick snappers. And super importantly, as we'll get into, to get the Vmax, you need to have a high concentration of your substrate, so that you have every enzyme has its maximum possibility. It's not getting held up by not having enough substrate, so it's not like you running out of substrate. And so when we're actually measuring the maximum velocity, we're getting it first. We take a whole range of concentrations, and this is also of substrate concentration, so we're doing individual velocity measurements, and then we're going to graph those and use those to find this Vmax. But so the Vmax is like the maximum speed that you can work at. You take a timer, go. We'll talk about some of the some of the assumptions we have to make and some of the time constraints that we have to work with so that we're in like the steady state. But if we do this and then we say, okay, take the amount of sticks that were formed, that were broken, and then we'll look at the time, we get this idea of this Vmax, so this maximum velocity. And then if we were to divide that by the number of snappers, we would get our kcat, so our turnover number. So like the goodness of the speed at which like a single enzyme copy is working, whereas the overall rate is going to depend on how many of those enzymes we have. So how many stick snappers are actually snapping the sticks, that's going to influence how many sticks get snapped. But you're also going to be limited by your substrate concentration, because if you have more stick snappers than you have sticks to snap, then you're going to run out of sticks. And so it doesn't matter if you add any more of your snappers, you're going to reach this plateau. And you're also going to reach a plateau if you have too many sticks to snap. And so basically in that case, you're going to saturate your enzyme. So each enzyme, there's way more sticks than enzymes, and so no matter how many more sticks you add, you can't speed up. And so by taking these examples where we have a really low substrate concentration, or we have a really high substrate concentration, or we have a really low enzyme concentration, or we have a really high enzyme concentration, we can use these extremes to kind of simplify the mathematical equations that we're going to use. And the mathematical equations that we're going to use are these Michaelis-Menten kinetics equations. And so I'm going to talk about how we actually derive that equation, where it actually comes from mathematically, as well as the implications of it for when we're, like, say, looking at things on a graph, and how we can experimentally determine the Km and the kcat for different enzymes and for different enzymes towards different substrates. And so one of the key concepts that's going to come out is that the Km, that Michaelis constant that we're talking about in terms of how, like, that affinity for the substrate, it's mainly the affinity. There's also some other, like, complicating factors, but you can think of it as like the affinity for a substrate. It's similar to, but not the same as Kd. So Kd, the dissociation constant, that's when we're talking about, like, things binding and unbinding and binding and unbinding. When we have the Km, we have to think about things binding and unbinding, and then also things binding and then being snapped, so being turned into product. And we have this constant called the Km that we that is then going to be determined by that. And so the Km is going to be work out mathematically is equal to the rate at the concentration of substrate at which you have your half maximal velocity. And so because remember the half maximal velocity is the maximal velocity is going to depend on how many stick snappers you have, but the constants are going to stay constant. This Km is going to stay constant. So the affinity isn't going to change if you have changed your number of sticks. And similarly, the kcat isn't going to change if you change the number of your sticks or the number of your enzymes. These are constant things about the enzyme and about the system. And so about, like, in these certain conditions with this substrate and this enzyme, these will remain constant even if you change those other things. And so by taking into account these factors, we can then determine these constants if we take the same enzyme concentration and we do a range of values of substrate concentrations and measure velocities. And then we can plot these out. And when we do this, we'll see that there's going to be a substrate concentration at which we have a half maximal velocity. And this doesn't matter what your concentration of enzyme is, as well as, I mean, like, unless you're at, like, really extremes. So this is, your Km is going to be constant. So you can measure out of any enzyme concentration, but different concentrations of substrates, and you get this curve. And these are the curves that we see on these Michaelis-Menten kinetic graphs. In this curve, you have a plateau where you run out of where you have too many sticks. You have more sticks than snappers, way more sticks than snappers. You reach this plateau where you're at your maximal velocity. And the concentration that it took you to get to that half maximal velocity, half of that maximal velocity, that is going to be your Km. If you have a higher affinity, that Km is going to be lower. It's going to take you less of the substrate to actually get to that halfway point. If so, something that has an enzyme that has, like, a higher affinity, so like a better, is going to be a lower Km. But the actual velocity is going to then depend also on how fast you're snapping the sticks and how well you can actually turn the sticks over from grabbing them to actually turning them into your product. And so this is going to be the catalytic, the turnover, the catalytic rate. constant. And so that's going to be your kcat. And so you can then get the kcat by dividing the maximal velocity by the concentration of the enzyme that you were using in your assay. So sometimes you also see this thing called the specificity constant, which is the kcat over the km. Sometimes you might see it called like the catalytic efficiency, but this can be misleading. I'll tell you more about this and how this various papers and stuff, but basically it can be misleading if you're trying to use it to compare different enzymes, but you can use it to compare the same enzyme with different substrates and see which ones it prefers. So I'll tell you about all of this, also some various caveats, things like this, as well as things like you might be introduced to Lineweaver-Burke plots, which have some problems that I'll talk about, as well as the fact that you have to be measuring in very specific conditions to get to these Michaelis-Menten conditions to get these equations to actually work, and that not all enzymes are actually going to obey Michaelis-Menten kinetics. You can have things like allostery, like we see with hemoglobin binding, oxygen, where binding to one subunit influences binding to another, and you can have all these complicated enzymatic schemes. But at the end of the day, for simple reactions, we can take this stick snapper analogy and put it to use. And the stick snapping might seem kind of impractical, but it's bringing me back to my undergrad when I was studying a neuropeptidase. So it was this enzyme that broke peptides. So it basically was a stick snapper where our sticks were going to be peptides, so these short amino acid sequences, like little proteins, but really, really, really short, and they can act as these chemical messengers, and this protein actually degraded those messages to help stop the signal. So pretty cool stuff, and I would measure it using these fret things, so it had a fluorophore on one end and a quencher on one end. So when it was uncut, you would get this quenched fluorescence because they're close together, and the quencher would be stealing the energy that would normally be given off as light. But then when the enzyme works, they break apart and you get this signal of light. And so I could measure this light, and I did this with different substrate concentrations, and that's how I determined the Michaelis-Menten constants and all of this various stuff for this enzyme. So this is taking me back to my undergrad days, and so let's take it away and get a little more serious, and I need to clean up the mess from snapping all of these sticks first.
So at their basis, these constants and everything we're going to talk about are involving thermodynamic principles. So basically the free energy in the various states, and giving the lower free energy is better. And so basically that's telling you that things are kind of happier. And so often our products are going to be happier than our substrates. And this is going to help us so that our reactions aren't going to go in reverse. But the enzyme itself is kind of helping you get there by lowering the transition state. So there's an activation energy in order to get to those products. And the enzyme is going to be helping lowering that activation energy in various ways, holding things together, various different things that I talked about in yesterday's post, and I plan to talk about more in upcoming posts. And so I'm not going to get into all of this, but this is going to help us make some assumptions that we're not going to go back and form our substrate from our products. And instead, we're going to consider the simple scenario where we have an enzyme bind to a substrate to get this enzyme substrate complex. And this is reversible. And so it can then unbind, bind, unbind, bind, unbind. And then it can also go to a product. So it can convert that substrate into a product, which can then be released. And this is the situation that we're going to consider when we talk about this Michaelis-Menten equation. And so we're going to be talking in terms of having this free enzyme and this free substrate, this enzyme substrate complex, and then the free enzyme and free product. So this is a typical type of graph that you'll see when you're talking about Michaelis-Menten kinetics. And so in this case, you have a constant concentration of your enzyme, and you're changing the concentration of the substrate, and then you're plotting the initial rate of product formation, this V0. And so each of these is representing a separate experiment that you did. And these experiments that you're doing, there you're measuring the velocity. So when we're talking about velocity, we're talking about the rate of product formation over time. And we'll talk more about how we actually calculate this rate and how these fits into how we're getting these constants that we're going to get. But the key thing is that in order to get those initial velocities, we have to do a bunch of experiments. And so we have to take an enzyme and we have to change the product concentration, and then we have to measure the formation of the product. A key thing is that we need to measure the velocity when we're in this steady state. We'll talk more about this steady state later because the steady state assumption is important for how we understand and how we're able to make simplifications when we're doing our calculation. And the steady state, just a little hint, here before, so no one gets confused. And so in terms of mathematically, the steady state is telling us that this enzyme substrate the concentration of this enzyme substrate is going to stay constant, so that every time the rate at which it's formed is the same as the rate at which it is unformed. And so it can be unformed by either just releasing it or by changing it into the product. And so the steady state assumption is that this is going to stay constant. By steady state, we're referring to, it's kind of like an equilibrium, but not. So at equilibrium, all of this would all of the concentrations of all of these various things would have to be constant on net, and we would have like a closed system where nothing is like being added or removed. Typically, for here, we're dealing with a steady state. So this is staying constant, but the concentrations of these are changing. And so we can have different concentrations of our substrate, so we can be losing the substrate and gaining the product, but this is staying constant. And so we have this steady state where this is staying constant. And this is going to be important for simplifying our Michaelis-Menten kinetic constants. So if we look on a graph, and typically what we're doing is we're measuring the product formation. And so this is going to be the green line. And so in the case of my peptidase example, what I was doing was I was measuring the stick snapping using that quench fluorescence assay. So measuring the giving off of light. And so I would set up my reaction tubes where I had the same amount of enzyme, but different amounts of that quench fluorescence substrate. And then I would measure the reaction in this early part in this steady state. So there's actually a little bit before this early part, and this is called the pre-steady state. And so with the pre-steady state, basically where the enzyme grabs up the substrate, so there's plenty to go around, but there's not much breaking going on because you have to actually like pick up the things. And then you have so the enzymes are kind of like finding the sticks to break, but then they get into their flow. And so in the steady state, the enzymes are doing the grab, break without having to worry about running out. And so remember, they're also, in addition to doing the breaking, they could also be doing the dropping, but then there's another one that they can pick back up. And so there's no concern about running out. But eventually you reach this post-steady state where you're running out of sticks to break. And so your free enzyme concentration starts to go up, and your bound enzyme goes down, and you're not making product anymore so this is cumulative product form. So you reach this plateau. And so you want to take the slope of this linear part before it plateaus, and this is going to be your initial velocity, the V0, or the V0. And so this is not the plateau that we're going to talk about when we're finding Vmax. This is just going to be the velocity this is just like the plateau at this one concentration of substrate. When we're talking about our Vmax, that's going to correspond to running out of like the enzyme, as opposed to running out of the substrate. So here we're running out of the substrate, and here we're running out of the enzyme. So we have more substrate than we have enzyme. And that is why we're plateauing here. And here we're plotting each of these different V0s from your different reactions. And we're figuring out the Vmax. And this Vmax is going to be a property that is going to come from this, include the Km and the kcat. And it's also going to involve the enzyme concentration, whereas the Km is not going to depend on the concentration of your enzyme. And so no matter what concentration of enzyme you measured at, assuming that it's within reasonable ranges and you're not in weird situations, then you're going to have this in the, this Vmax is going, the half point is going to be equal to your Km, the substrate concentration at which you reach that half maximum velocity. But your maximum velocity, if you had a higher, like enzyme concentration, your Vmax would be higher, but so would your half Vmax. And so you're still going to be at the concentration. So you could think of kind of just like stretching this up. And so this is going to then allow us to figure out these things. And note that here we can, when we're talking about velocity, we're going to be talking about, we can talk about the velocity at any one point. And so this is the velocity at any one point. And here you can see that it does matter, the substrate concentration does matter, but when we're talking about the maximum velocity, then the substrate concentration doesn't matter, because basically you run out when you reach a point where you're at the maximum and you can add more substrate and it's not going to influence anything. But in either case, you're going to have this Km matter. And so let's talk more about what this Km actually is. So first, where does it come from? We'll talk about where, like the mathematics, like how this is derived and everything. But this work was carried out. It was published in 1913 by Leonard Michaelis and Menten. It was published in German, but there is now they did a translation of it in English. So Johnson and Goody, this is a Goody article. They do this translation and also kind of like a modern day interpretation of it. So really good stuff. But I always like to bring up Menten because often, like, you don't know, oh, like not many equations are named after women. And so it's nice to have this. One of the most important equations in biochemistry come in part from a woman, and she's a phenomenal woman at that. So she was born in Canada in 1879. She became one of the country's first female medical doctors, but there were limited opportunities there. So she moved to the US and she worked at the Rockefeller Institution. Then she moved to Germany. And then she moved back to the US and got a PhD at the University of Chicago. Then she went to the University of Pittsburgh and then British Columbia Medical Research Institute. And she had this phenomenal life inside and outside the lab. And so she was a skilled musician and artist and spoke 6 languages. So yeah, so you might think that, oh, she must be German. She spent all her time in Germany. No, she was born in Canada, and she just spoke 6 languages. So amazing person. And yeah, so she passed away in 1960, but her name is always remembered through this Michaelis-Menten kinetic equation. But people, because you just see the last name, you don't know, oh, hey, that was a woman. So I like to bring that up just because there aren't many equations named after women, and it's important that we recognize the contributions of women. And so Menten, yay. Okay, so now let's dive into this equation that they came up with. I can't deprive you of the derivation of the Michaelis-Menten kinetic equation. So this is how you normally see it written, and this is what I was showing you in that picture before. So you have V, so this is a velocity, equals the maximum velocity Vmax times the substrate concentration over the Km plus the substrate concentration. So you have the velocity V equals Vmax, so the maximum velocity, times the substrate concentration over the Km plus the substrate concentration. And it's this equation, and the Km is just going to be this. We'll see the Km in a minute, but the Km is kind of going to be the simplification of these rate constants. So we kind of have these rate constants. We have this K off, this kcat, and this K on, and we're kind of going to lump them together because they're all constants. We'll lump them together and we'll call them this one term Km. And this is going to be where we're going to get this. And we'll see where all of this comes from. But at first, it's important to kind of just talk about what these things are and kind of like the differences between a rate constant and a rate. So a rate constant is going to be constant in terms of an enzyme and the substrate and the conditions. So basically, it's something that's inherent to the system that you're working with, the enzyme, the substrate, the buffer, all of this various stuff, but it's not going to depend on like concentrations of things. But some things are going to depend on concentrations. And so when we talk about like rates, those are going to depend on concentrations. And therefore, by measuring the things that depend on the concentrations, so by measuring things like velocity, we can then, which has this impacted by the substrate concentration, then we can kind of use that to figure out the constants, the things that don't change, by changing the things that do change, and then measuring that and seeing what was the constant. And so this is how we can get things like our Km out of this. And then Vmax, remember, that's going to be telling us about our catalytic rate, because this is going to be our Vmax divided by our enzyme concentration is going to give us our catalytic rate, because the Vmax is telling us, like, if you had all of these copies of an enzyme, how fast would this go? But the more copies of an enzyme you have, the faster you're going to go, even though the individual turnover, the individual like turnover rate of a single copy of the enzyme would be lower. I mean, it would be the same no matter how much of the enzyme you actually have, because these things are kind of inherent to a single enzyme copy, but we're not measuring a single enzyme copy, we're measuring a big population of enzymes. And so that's when those things are going to come into play. But first, let's just talk about these rate constants. And this, so we talked about how the rate constants are going to be constant for the equation. And remember, the Km is coming from these rate constants. We're going to define the Km to be these K off plus kcat over K on. And so these are going to be our rate constants that are going into that equation. And so when we talk about rate constants, we're going to, basically that's going to be like the speed. So if these, what rate are, in order for this to happen, in order for product to be formed, you have to first form this intermediate, this enzyme substrate complex. And then this enzyme substrate complex can be turned into product. We're going to simplify things and kind of, we're just going to consider, we're not going to consider that this enzyme product is going back into substrate. So this goes back to what I was talking about in the beginning with the free energy, how typically the free energy of the products is going to be so much lower that this isn't going to go backwards.
Also, because you're measuring these like initial velocities, you also, that negates having to worry about product going back into the substrate, because you don't have product to go back yet. So you have to build up a bunch of product before you can have any sort of thing like that. Also, in some cases, the product can actually inhibit the formation of more. And so, but yeah, but with the initial velocity, we don't have to worry about this stuff.
And we're going to be, so we can care, we don't, instead of putting on like another, instead of making this a reversible thing and then having like a forward arrow and a backwards arrow and that sort of thing like we have for this, we're just going to consider a forward arrow, and we're going to call this the kcat, the rate constant for when we're going from the enzyme substrate to the enzyme plus product. We're also going, and you'll see in the simplified version when we talked about the stick snapping. So you also, in order for the enzyme to do it again, it's actually going to have to release this. And so for some enzymes, for some reactions, this can actually be the slowest point. The speed at which this reaction is going to happen is going to be limited by its rate limiting step. And so sometimes you could have instances where the rate limiting step is actually the product release. And for example, you might even need to hydrolyze ATP in order to release the product and get this going again. But we're going to simplify things and consider, we're going to skip over this part and just consider that the product, the actual doing the product formation is going to be making the product is the rate limiting, and then we're not the actual product release, and then we don't have to consider this EP, intermediate EP, before the E plus P. So we have this amount of our enzyme substrate complex is going to be determined by this K on, so the forming this complex, the K off, just like letting go of this complex, and then the actual converting it into product. And so ES is going to be dependent on these three parameters, K on, K off, and kcat. And this is going to be reflected in this value, this Km. And so the Km is basically the more likely they are to be together, the higher the affinity, the lower the Km is going to be, because the less of the substrate you have to have in order to form this. But then you also have to consider the kcat. And so the kcat is going to be when you're taking your enzyme substrate and you're converting it into product. So this is also going to affect this enzyme substrate concentration. And when you're at a steady state, in this steady state assumption, we're basically saying that the rate you're forming is the same rate as you're coming apart, either because you just let go or because you form a product. And so this is going to be the steady state assumption. And the rates are the same, but not the concentrations. And so we could have you can have this, basically, you can be depleting your substrate and forming product. So it's not a true equilibrium, but you have a steady state where you have this constant concentration of the intermediate ES. Speaking of concentrations, we can represent the concentration by sticking them in brackets. And so when we talk about the enzyme concentrations, we're typically talking in some sort of like molarity, millimolar, nanomolar, picomolar, micromolar, some sort of molarity where we're talking in like copy numbers. So mole is mole 6.02 times 10 to the 23rd per liter. And typically we're talking about a lot lower values of that. And so then we're using these like metric prefixes that make it smaller. But in terms of the units of the rate constants, so K on is going to have units of K of 1 over concentration times time. So this is going to depend on concentration and time, and then K off is going to depend on time and 1 over time. And then K cat is going to be 1 over time, just in terms of where these things are coming from and how you're going to see them in your equations, and things are going to cancel out and various things like that. Okay, so rate constants versus rates. So rate constants, so remember this is like our kcat, our k on, our k off. These are not going to change depending on the concentration, because these things are values that are inherent to like your enzyme substrate system, buffer, all of that stuff, temperature, various things. But the rates at which they're going to, the rates at which the concentrations of the various players are formed will change depending on concentration, because those rates depend on the concentrations. So the rate, remember, is like what you're actually seeing, what you're actually measuring. So if you give a bunch of stick snappers sticks, and then you're measuring how many sticks get snapped over time, that would be like your rate. Whereas the rate constant is going to be the things like how well, like for an individual stick snapper, how good is it at grabbing sticks and how good is it at converting those sticks to products. And so those are not going to change depending on concentrations of things, because those are like inherent to that single copy. But if you have a lot of copies, if you have different concentrations of sticks available, then you're going to see differences. And so the actual rates that you're measuring are going to change. So usually we measure the rate of product formation, so increase in P over time. So you might see this as like dP, or but how much product you can make depends on how much ES you make and how well that gets converted to EP. So we have our rate of product formation is going to be our rate of product formation is going to be kcat times the concentration of ES, but ES is going to depend on ES formation, so K on times the concentration of E times S, times the concentration of S, and then also the ES break it down. So there's one way to make it, but there's two ways to lose it. So you can just let go, and this is our K off, or you could turn it into a product, and this is our K cat. And this is going to be multiplied by the concentration of ES. And so if you've done chemistry, if you've done that sort of thing, rate constants, you see these type of things a lot, where it's going to depend on the rate. The rate's going to depend on the rate constant times the concentration of the things that it depends on. And so if you depend on two things, like you're depending on the concentration of your enzyme and the concentration of your substrate for the ES formation, then you have to multiply these by each other. Whereas if you only have one thing, then you have like this unimolecular rate constant where you're only depending on the concentration of this one thing. whereas this would be like a bimolecular because you have two things. Okay, so now let's look at the actual rates. So these are things over time. And so we can have our change in substrate concentration over time. And this is going to be equal to, so our K on, so how much we make it, and then our how much we so our change in free substrate over time, this isn't going to be the same as the rate at which ES is broken down. This is what we're talking about here is when we're actually just like letting go, because if you break the substrate into product, then that is not going to give you more free substrate. So instead, what we're talking about when we have this free substrate concentration, this is going to depend on the rate at which you are forming. So you lose free substrate by forming this. So you lose free substrate by forming ES, and then you gain free substrate by letting go of ES, by letting go of it without actually turning it into product. The change in your free enzyme concentration over time, this is going, your free enzyme can be, remember the enzyme isn't going to get used up. It's not going to, it'll be regenerated, but it can be like occupied. And so the free enzyme is enzyme that's not in use. And so basically this can happen if you can lose it if you have it bound to a substrate. And so then you can gain it back when you break down this enzyme substrate complex. And this is where we get into this, there's two ways to lose it where we have this. Then you'll see that to change the change in the enzyme substrate over time, this is going to be similar but opposite. And so we gain it if we have this with this K on times the enzyme times the substrate. So we gain it when we form it, and then we lose it when we break it down. Here, when we broke it down, we were getting our free enzyme back, but here we're taking, we are basically losing our enzyme substrate complex. And then finally, we have our change in product formation over time. And this is going to be equal to our kcat times ES, because there's this one way to make the product. You take your enzyme substrate concentration and you multiply it by that kcat, so that this rate constant. Okay, so now that we have these definitions and we can define things in terms, we can define these rates in terms of rate constants and concentrations. And we go back and we do that, now we make that a steady state assumption. And so our steady state assumption, remember, is that the concentration of your enzyme substrate complex is constant. And so it doesn't mean that nothing's going on. It just means that at the same rate that it is being formed, it is breaking down. And so because we have, it's made, we have the change, so we can say that the change in the ES over time. So we remember that this was, we defined the K, here we saw that the change in ES over time is going to be this K on times E times S minus K cat, this thing. And so we saw that because this was representing forming it and then breaking it either by letting go or turning it into product. And now we're saying, okay, we're going to say that the change in this over time is going to be 0. Okay, and so what we're trying to find is the rate of product formation. And so we want this kcat times this concentration of E times the concentration of S. And now we're saying, okay, well, if we're relying on that concentration of ES, now we're going to say that the concentration of ES is going to be constant. So basically we have this, when we rewrite it like this, we now want to be able to isolate this ES because this is what we're going to need in order to determine the rate of product formation. So we need to isolate this value. We know that the total amount, the E we put in, so E total, and we know that any E that's not bound to the substrate has to be free. So our total enzyme concentration is going to equal the concentration of enzyme bound to substrate plus the concentration of free enzyme. And we can just rearrange this in order to then have our free enzyme defined in terms of the total enzyme minus the enzyme substrate complex. And why is this important is because we know the total amount that we put in. And so we can basically simplify things by not talking about the free enzyme and talking in terms of the total enzyme. So now we just have to think in terms of the total enzyme and in terms of the enzyme substrate complex. And now we just plug this into our equation. So where this E was, we now put in ET minus ES. And then so everything else stays the same, but then we just factor this out and we do a little rearranging. And so we get something that looks like this. And now we're just going to shift it around to put the ES's on the same side, because remember the ES is what we're going after, because that's what we need for our product formation. So when we shift things around and then we put them together and get them by themselves. So this is all just some like algebra rearranging things. I encourage you to actually like go ahead and actually do this derivation yourself. It can be really helpful. See where things are actually coming from. So that was one of the reasons why I made these this was several years ago when I made these, but I was wanting to derive it, and it's because I found it helpful for myself. Okay, so basically now you want to isolate this ES. And now here I just flipped what was on what side so that ES was on the left to make things easier to see. And here's where we're actually getting to Km. And we're actually basically saying, okay, we're going to define Km as this, we're just going to lump this thing together and call it Km. And so we're going to call this Km is going to be the K off plus the Kcat divided by the K on. And when we do this, now we can basically simplify this and get this nicer looking equation where the concentration of ES equals the concentration of the total E, which remember is what you put in so you know how much E you have, times the concentration of the substrate, divided by the Km plus the concentration of the substrate. And now we have the ES we need for our velocity equation. Note too that when we're looking at this Km, so K off plus Kcat. So this is where we're losing our enzyme substrate complex, either because it falls off or because it gets turned into product. And this is going to be divided by the K on. So the bigger the K on, the better you bind, the tighter you bind to something, the faster you bind to something, these various things. This is going to basically, so this K on, like how fast you're actually binding to the thing is actually going to, the bigger it is, the smaller Km is going to be. And so the higher your affinity, the smaller Km is going to be. So either because you bind it quickly or because you don't let it off that easily. So if this was bigger, so if this was smaller, then this number would be bigger. And if this was bigger, if this was smaller, this number would be smaller. And if this is bigger, then this number would be smaller. But you can see too that Km is also going to depend on kcat. So it's not like a totally independent thing where it's just telling you about affinity. But this is the Km, and it's sometimes called like the Michaelis constant. Okay, so now we have this, we can stick it into we have this way that we can talk about the concentration of ES, and now we can put that into our velocity equation. And so velocity is going to be the change in our product formation, the concentration of the product over time. So we take what we know, where we have this velocity equals this kcat times the concentration of ES, which we just defined as this. And now we put them together and we get this relationship. And this is going to work for V at any concentration of substrate. But something special happens when you have a lot of S. So the maximum velocity, this Vmax, is going to occur when you have so much substrate that the enzyme is saturated. So all the enzyme is bound, and therefore E total equals ES. And so we don't have to worry about all of that other stuff. So remember, E total is what we know. And if we assume that all of the enzyme is then occupied, then we don't have to worry about the other stuff, and we can just consider that ET equals ES, and therefore the kcat Vmax is going to equal kcat times ET. And so basically the amount of enzyme you have is going to times the kcat is going to give you your Vmax, which is why when we find the Vmax on our graph and then we divide it by the enzyme concentration, we can get our kcat. So remember that the kcat is telling us about kind of like a single enzyme copy. And then in order to know the maximum velocity, we need to be able to multiply that by the concentration of the enzyme. Then we can rearrange this to get our E total equals Vmax over kcat. And then if we write it like this, now we can substitute E total for ES, and we can define the velocity at any substrate concentration in terms of Vmax. So Vmax instead of V. So now we can define the velocity at any substrate concentration in terms of Vmax. So we take this ET and we exchange it for Vmax over kcat. And then we can basically cancel the kcats out. And we get this equation, which is how you normally see the Michaelis-Menten equation, where you have velocity equals Vmax times substrate concentration divided by your Km plus your substrate concentration. And so this is how you commonly see the Michaelis-Menten equation. So when we plot this on the graph, we see that the Km is the concentration that's going to get you to half of the Kmat of the Vmax. So why is this? What is happening that is special when you have the Km equal to 1/2 of the Vmax? Okay, so when you're at half of your Vmax, if we put, so remember this equation is going to be like, so the V is just like any velocity, like your velocity under these conditions. And then your Vmax is going to be the maximum velocity, which remember we get when we run out of, when we're basically saturated our enzyme. So each enzyme is working at its maximum capacity. And then what happens if our velocity, so what we're actually measuring in these conditions, is equal to the half of the maximum velocity. When we do this, we put in half of Vmax for our V. Now these are going to cancel out. And then you just do a little math and rearranging things. And you get that the Km now is equal to the substrate concentration. So this is saying that why the Km is going to be the concentration at which you get half of your Vmax. And so the lower the Km, the less substrate it's going to take you to get to that point. And so remember that basically how fast you're working is going to depend on how good you are at like binding and good you are at converting it into product. And so the better you are at like binding it and stuff, the less substrate concentration you need in order to like have to reach that point where basically you're relying on your turnover rather than like relying on having to like scrounge up these Kms. And so this gets to an important point when we're talking about something called like the specificity constant, or your catalytic, sometimes called catalytic efficiency. And so this takes basically Km and kcat are telling you, they can kind of be telling you different things. So Km is telling you typically more about the affinity, whereas kcat is telling you more about the actual changing it into substrate. But remember that Km is not independent because it also depends on the kcat. But the Km at a lower concentration, then the Km is going to be more important because it's more important. That's kind of going to be your limiting, is actually binding to the thing. Whereas if you had a lot of it around, even if you didn't bind that well, then the Km isn't going to matter that much. And so people often want a way to kind of take into account both Km and kcat because they're both important properties of an enzyme. But if you can't just like directly use this specificity constant in order to compare different enzymes. And so this is a really good article by Eisenthal, Danson and Ho, published in Trends in Biotechnology in 2007. And basically in this chart, they're showing that if you can reach the same specificity constant, so the same kcat over Km, with different values of Km and kcat, and it's going to depend greatly on the substrate concentration. So if you're using it to compare different enzymes, you can run into trouble because the same enzyme, if it can have like a basically a enzyme having a higher catalytic efficiency, so the kcat over km can at certain substrate concentrations catalyze a reaction at lower rates than one having a lower catalytic efficiency, because it depends on your substrate concentration. And so they're recommending that you only use this to compare the same enzyme with different substrates. So as this like specificity constant, so does the same enzyme prefer this substrate, or does it prefer this substrate, as opposed to trying to use it to actually compare different enzymes. And so then people have suggested other types of ways to actually better compare enzymes together. And I'm not going to get into this. I'm not like an expert on this. That was something I always remembered, was that this value should be used cautiously and not be like overinterpreted. And it's important to look at both the kcat and the km when you are thinking about how an enzyme works. Another couple of words of caution. And so not all enzymes are going to follow Michaelis-Menten kinetics. And so sometimes you might see enzymes that instead of showing just like that nice simple plateau, you see something where you have something curvier. And this can be indicative of allosteric effects or like cooperative, and this can be indicative of like cooperative binding, cooperative action of some sort, such as you see with hemoglobin, where hemoglobin has these 4 binding sites for oxygen, and once one binds, then it influences the binding of the others. And so you get this curved shape line. Speaking of the shape of lines, in order to actually get information from one of these graphs, when you do this work and you make this graph, typically you never actually reach the actual plateau. You just kind of get really, really, really close. And so you kind of have to estimate what is the Vmax if you were just to do it by eye. These days, the best thing to do is to actually use a software that's going to use a like nonlinear regression to actually fit an equation to this line and determine the Vmax that way. So that is like the best way to do it, to my knowledge. But sometimes people, especially in, this was especially common before we had as powerful of software to do those equations, use this like Lineweaver-Burke plots. And these should be used with caution. And so basically what these do is they try to turn that curvy line into a straight line. And they do this by basically, instead of measuring substrate concentration, velocity, the velocity, what they're doing is it's a double reciprocal plot. And so you measure 1 over substrate concentration and 1 over velocity. And when you do this, you get this line. When you do this, when you look at this line, now you have your interceptions. Your intersects are going to tell you things. And so this point here is going to be your -1 over km. And this point, so your x-intercept and your y-intercept is going to be 1 over Vmax. And then the slope of the line is going to be km over Vmax. The problem with this is that you can see that all of these points are really clustered together and all of these points are really far away. So the high substrate points are going to cluster towards this, towards here. And so each of these points has less influence. Whereas the points that are farther from the origin, so points that say like at a low substrate concentrations, remember, because this is inverse. So if you had a higher number, this would be smaller. If you have a lower number, this is going to be bigger. When you have these numbers all the way out here, well, now they kind of have more influence, because you can imagine if you had like 1 point down here, it would really draw this line down. Whereas if you had little differences here, they're not going to matter as much because there's all these other points here. Whereas here is kind of like you have a lever and you're kind of like pushing the lever. So if you have any experimental errors, these are going to be amplified. And so these are reasons why it's good to use this like the nonlinear regression to actually just try to get the values from the curve directly. but you do commonly see these seen, and so I just wanted to introduce people to them. So I hope that was helpful, and I hope that you also remember that Michaelis-Menten kinetics, the Menten is for Maud Menten, and she was a really amazing scientist. And yeah, so enzyme kinetics. Whew.